Well, hello everyone. I hope you all having a good evening. And today we're starting the first keynote session of the Brazilian Symposium on Synthetic Biology. I hope this evening finds you all very well. And today we're having the amazing Emily Leproust. These sessions that we're having right now, they're optional, but we strongly recommend you to attend them as the themes we'll be talking about are extremely interesting and important for the synthetic biology in general. Again, if you all have any doubts, please send them on the YouTube chat in either Portuguese or English so that our moderators will be passing on to the speaker. So today we're welcoming the amazing Dr. Emily Leproust. So before she starts, we would like to introduce Emily to you. She, as an early pioneer in the synthesis and sequencing of DNA, Dr. Leproust is disrupting markets to enable the exponential growth of DNA-based applications, including chemicals, materials, diagnostics, therapeutics, food, and digital data storage. And in 2020, Bio presented her with the Rosalind Franklin Award for Leadership. Foreign Policy named her one of the 100 leading global thinkers. And Fast Company named her one of the most creative people in business. And prior to Twist Biosciences, she held escalating positions at Agillion Technologies, where she architected the successful SureSelect product line that lowered the cost of sequencing and elucidated mechanisms responsible for dozens of Mendelian diseases. She also developed the oligo library synthesis technology, where she initiated and led product and business development activities for the team. Dr. Leproust is designed and developed multiple commercial synthesis platforms to streamline microarray manufacturing and fabrication. She serves on the board of director of CM Life Sciences and is a co-founder of Petri, an accelerator for startups at the forefront of engineering and biology. Also, Dr. Leproust has published over 30 peer-reviewing papers, many on applications of synthetic DNA, and is the author of numerous patents. She earned her PhD in organic chemistry from University of Houston and her master's in industrial chemistry from the Lyon School of Industrial Chemistry. Welcome, Dr. Emily. The floor is all yours.
Thank you very much, Lisa. It's great to be here. Hopefully you can all see my screen. And it's my great pleasure to be here. Thank you so much for the invitation and the introduction. Today I'll give you a brief overview of what we do at Twist. And I'll start by saying the company. So I will be making some forward-looking statements. I'm very excited because I truly believe that DNA is changing the world for the better. And our customers are using DNA for amazing applications. I'll just give a few highlights. First, our customers are using DNA to engineer plants. And here on the left, I'm showing you teosinte, which is the native form of corn. And this is fully engineered corn over 10,000 years. But now we can accelerate engineering of food to increase traits that are good to lower the need for water, to improve resistance to disease, and of course to increase yield. Our customers also still in the area of plants have been able to engineer bacteria to deliver nitrogen at the root of plants. And that lowers the need for fertilizer, which lowers the cost of growing food, and is also more sustainable. Our customers are engineering yeast, algae, and E. coli to produce chemicals. So instead of extracting oil from the ground and producing chemicals that we need, but that are unsustainable, now we'll be able to make those same chemicals through fermentation of sugar, which is more sustainable, but also is cheaper and will enable the production of new chemicals that you could never do from oil, such as, for instance, spider silk and other material. Our customers are also engineering cells to create new therapies. And so they engineer cells, they create new antibodies, new form of biological drugs, such that in the future, diseases like cancer could become a chronic disease. So there's lots of great things that can be made thanks to DNA and synthetic biology. And last but not least, I'll talk very briefly about that at the end, but you can even use DNA to store data for the long term. And so really the secret to Twist, to being able to do all of this, is really an innovative platform that we've developed to write DNA. Here on the left, I'm showing what everybody else does. People use the 96 well plate to make 96 oligos, and you can assemble 96 oligos to make one gene. And it's good, it works, but it's expensive and it does not scale. At Twist, what we've done is we've developed a silicon chip where on the same size as a 96 well plate, we can produce 1 million oligos. So instead of 96 oligos, we have 1 million. So it's 10,000 times more oligos. And those oligos are grouped into clusters of 100, which means that we can make up to 10,000 genes on the same silicon chip. And that means that we make all the products for all the customers at the same time on the same chip. And so there's a lot of information. And so we had to build a big software infrastructure to keep track of all those orders happening at the same time. So the reason why we did that is because making a gene for synthetic biology is a very well understood process. Here from 1995, Dr. Pim Stemmer started from 56 of 40 base pairs. And if you have the right oligos, the right sequence, they will bind to each other. And if you have the right enzyme, you'll be able to create, in this case, a 900 base pair insert. And then on the right, starting from 134 oligos, again, with the right sequence and the right enzyme, he was able to build a 2.7 kb insert. So to make a gene, you need about 100 oligos. And the synthesis of one oligo, the chemistry is well understood, is well known. You start from a solid support with an OH group, and you do the addition of the first base. So using a phosphomylate, you can create a P3 phosphate bond. And I'm sorry, the quality is not that great. And then you can oxidize this to create a P5 phosphate bond. And this is the exact chemistry, exact backbone as you find in nature. But the 5' end is blocked with a blocking group. And so you can deblock that group to recreate an OH. So at every cycle, you add one oligo, and you can repeat that cycle as often as you need to build multiple bases and to build an oligo. So what we've done at Twist is we've been able to, on our silicon chip, do this cycle 300 times and being able to build 1 million oligos at the same time. Again, there are groups in clusters of 100. So based on that, we can make a number of products. And in the next few slides, I'll first talk to you about the impact that we can have. And then in the last 5 minutes, I'll briefly describe what those products are. So first, one of the things we can do with DNA is we can help respond to the global pandemic that we are in. COVID has been definitely very bad for many communities, for the economy. There's been tremendous human suffering, but we've seen that the scientific world has come together to help find some solution. I'm happy to share with you 3 of the things that at Twist we've done. And so the first thing we've done is we've developed NGS panels. And we all know that most testing against COVID was done by PCR, which is great. But PCR only gives you a yes and a no answer. But with NGS, we're able to sequence the entire virus. And so what that means is that we can get 100% coverage of the virus, and we can help scientists detect which variants are taking off, and help scientists follow the evolution of the virus. And our panel, our NGS panel, has received FDA emergency authorization. The thing that we've done is we've created synthetic controls, because if you're developing a PCR assay or an NGS assay, you need COVID in a tube to know if your test works. And growing COVID is very dangerous. And so we've created a fully synthetic RNA version of COVID. So it's a full 29,000 base pairs. It's cut in 5 pieces. It's RNA. And that has been very useful for our customers to demonstrate that their test works. And just last week, we launched the Delta version of the COVID as a positive control. And last but not least, we've also developed antibodies against COVID using our own platform. And for instance, those are the top antibodies that we have. And in a hamster model, we were able to show that as low as 1 milligrams per kilogram of antibodies was protective against COVID. So definitely those tools are available for the world to use. The second thing that we try to do with our platform is to advance human health. And we do that in multiple areas. The first area is in target identification. So as you know, in order to develop a drug, you need to know what is the target for a disease. And CRISPR has become an amazing tool to identify targets. And so what you can do is you can design a genome-wide experiment where you can silence many locations in the genome, at which we will synthesize it for you, and we'll give you the guide RNA, and using a viral particle, and our customer can transfect cells, and by monitoring over time which cells survive, they're able to detect which genes location, which genomic location is important for that disease. And that way you can associate locations with diseases. And in this example from the Sanger Institute, using twist oligos, they were able to study 300 plus cancer cells, and they were able to find the right target for multiple cancer. So that works really well. And the next frontier of target identification is not to just use one guide RNA, but to make multiple guides together. So for instance, if you could have a guide to silence a first gene, an guide to silence and a second gene, you'll be able to look at synergies or association between those two genes. And so that's the very long twist. We can make oligos they are able to silence multiple genomic regions at the same time and get a much finer understanding of the biology. And there's been a number of publications that way. So our oligos are absolutely critical nowadays in the discovery of new targets. Once you have a target, you have to find a drug. You have to discover a drug. And typically, to do that, you need libraries. You need to screen many different mutants. And so one way to create mutants is through random mutagenesis, which is very inexpensive, it's cheap, but it's only one base change. And if you wanted to do a move from a codon that is an AAA codon, G codon, you could never do it. So mutation is inexpensive, but you can't explore the sequence space. Another way to do it is to use an NNN synthesis. So at least there you make a codon changes, so 3 bases change at a time. But with NNN and NNK, you have a very imprecise control of the changes. You still add stop codon, and you actually end up with a lot of bias. And so we think there's a better way, and the better way is in the computer. You do the mutagenesis. You send us a file, and you say, those are the codons I want to change. You can have one codon, you can have multiple codons, you can have domains, multi-domains. And so if you can write it in a computer, we will be able to make the change. And the reason that is because we use our silicon chip as the source of mutations. And so we'll make oligos for each mutant that we will incorporate into your template. And thanks to our oligos, you can have precisions that are base by base. You can control the codon usage. You can have very precise combinatorial diversity. You can choose the ratio of different amino acid. You can change the length, for instance, of a domain. For instance, a highly mutation domain, a CDR domain, could be changed in length. We can remove restriction size that you don't want. We can remove bad motifs. And we can even do those mutations on many different scaffolds. And last but not least, 100% of our libraries are NGS verified, so we can prove to you that in the tube, you have exactly the sequences that you wanted in your file. So it's very precise. And so in conclusion, if you compare libraries made from our oligo pools compared to NNN, NNK, or TRIM, you get the full control over your amino acid distribution. There are no stop codons. There are no out-of-frame mutations. You can remove live, and you can match the human repertoire. What that means is that now that billions of antibodies have been sequenced, we know the rules of the human repertoire, and you can create mutation that follow those rules. And what that means is that when you do your screen to discover your antibodies, you'll be able to make sure that 100% of your sequences are fully human and human-derived, which means that you will not have immunogenicity. Once you have discovered your antibody, we can help you optimize your antibody. And so if you give us a starting antibody, we'll be able to, using our Twist antibody optimization platform, we'll be able to help you develop biobetters. We'll help you to humanize an antibody. And we've shown that we've also been able to support our customers to have to discover drugs against hard-to-drug target. In addition, what I've talked so far is where we provide you reagents and you do the work, but actually we can also do the work for you. And so if you send us a target, we'll be able to do the discovery for you, we'll be able to optimize, we'll be able to do preclinical development, and we'll even be able to do the IND and clinical development if you want. And so the idea is we provide reagents and tools for you to do the work, but if you want, we can also have a premium offering where we do everything for you. A little bit more details around our pharma offering. because we can make a lot of library in-house, we have on-the-shelf libraries that are recapitulating the human repertoire called hyperimmune. We have smaller antibodies, single domain. We have GPC antibodies. We have libraries against ion channels, carbohydrate, ancestral, and we even have cow antibodies if that is needed. So with all of that, we've been able to sign 21 companies are asking Twist to develop antibodies for them. And actually, if you look at the modality of the programs that we have, is very diverse. We have some antibodies, we have some bispecific, we have some VHS, we have some ADCs, we even have some TCR, so very broad modality. And then the programs that we are working on for our customers are in the area of autoimmune disease, immuno-oncology, cancer, dermatology, neuroscience, and we even are developing antibodies for cats and dogs for our customers. And last, around biopharma, we also have our own targets that for which we have developed our own antibodies. And some of those are really hard. PD-1, TIGIT, CD3, A2A, those are really, really hard targets. And we have antibodies that are available for licensing for our customers. So to recap so far, in advancing human health, we've talked about target discovery, and we've talked about antibody discovery and antibody optimization. The next thing we can do in advancing human health is in disease profiling and detection. Being able to say, this is a patient DNA, what is going on with that DNA? We can do that too. And we enable a number of applications. One is just a germline genotyping analysis. So basically, the analysis of rare disease or the discovery of rare disease mutation. We can also do somatic or cancer detection. We can enable our customers to do circulating tumor DNA. So you may have heard it as a liquid biopsy. Recently, we've added methylation. So many different areas of disease profiling and detection that we can enable. And the way we do that is by doing what's called targeted sequencing. Right? So we're not reading the entire genome, but our customers are saying, here is dark blue box, those are the regions I want to read. For instance, I want the exons, or I want those genes, so I want chromosome 1. And then we're able to make DNA to provide coverage in those regions and provide no coverage outside of those regions. And that reduces the cost of sequencing tremendously. And so in the case of liquid biopsy, for instance, you could not do a liquid biopsy for the entire human genome. It would be too expensive. But you could do a liquid biopsy analysis for maybe 50 genes, the 50 top cancer genes, and that is what we enable. The reason why we are better is that the sequencing of those regions, you need one oligo per regions that you want to sequence. And so typically you have to make hundreds of thousands of oligos. And so when we synthesize hundreds of thousands of oligos and we sequence them, they actually have a uniform distribution compared to GC. But our competition, when they amplify those oligos, they create bias. And here in this case, you have a high GC bias. And so that means that some regions of the genome will have less coverage, and some regions will have too much coverage. However, with our platform, we're able to amplify those oligos uniformly, and so that means that you can do a uniform capture. And that has been quite useful to our customers. And so what that means in practice, that means that if you do NGS with Twist compared to other customers, other technology, other platform, you can reduce the cost of sequencing by half. That is huge, because if you're going to do a if you're going to a liquid biopsy assay where you have to sequence down to 50,000 X coverage, the cost of sequencing is enormous, and by choosing Twist, you will cut that cost of sequencing in half. The second thing is that you need to develop new panels all the time. As new scientific information happens, people need to update their panel. And with Twist, we can customize new panels in half the time as the competition. So there's a huge advantage to switching to us. And so far, commercially, it was easy, or it was available to detect SNP, so single mutation. It was possible to detect rare the genome, and now with Twist for the customers to detect methylation status. In cancer, methylation of genes or methylation of regions is very important. And now we have a all-included library prep and target enrichment for the detection of methylation, which is greatly appreciated by companies. So to conclude, in terms of advancing human health, as we mentioned, there's multiple areas of target identification, target validation, drug discovery, drug development, and disease monitoring. And the products that we have are useful in all of those areas. And so that means that we can offer to our customers, from the research all the way to the clinic, a suite of products that enables them to advance human health and advance the human condition. The next part I want to talk about is something slightly different, is how to use DNA to enable the future of sustainable data storage. And I like to start that portion of the talk by taking an example of, this is a picture from the lunar orbiter, and that is picture of the Earth and the moon in the front. So it's not the moon rise, it's the Earth rise. And NASA took that picture in the 60s, and a few years ago they decided to go back and try to find that picture. And so they had to find the tape, they had to find a machine to read it, they had to rewrite the software. And when they got the data back, the picture is not good. It's because magnetization of the tape over years degrades. And so there is a need for a better archiving of data. And DNA is our hard drive. And we believe that DNA is a better medium to store data for the future. And DNA is permanent. So we heard the news of mammoth DNA that was 1 million years old, that was sequenced. That was DNA in the ground with bacteria, with fungi, and after 1 million years, it's still working. The density of DNA is massive. You could put all of the data on the internet into a shoebox if it was made of DNA. For when you need a file to read a file back, you can use PCR for random access. And then finally, DNA is a universal format. We will always know to read DNA, and that's very different than media that we use. For instance, when I was young, we used VCRs, and now you can't read VCRs anymore. Maybe today still read a CD ROM disk, but probably in 50 years there'll be no way to read a CD-ROM. And so, but DNA will always be there. So quickly how that works, if you have a file, it's a bunch of zeros and ones, and in the computer you can encode that into ACGT. You can synthesize the DNA on our silicon chip. You can store it for 1 week, 1 month, 100 years, 1,000 years. And if you need the file back, you can PCR your file, sequence it, and get your file back. We have done dozens of demonstrations with Microsoft, with Netflix, with the United Nations, with many other, and it always works. And so right now it's still a little bit expensive, but we're working at Twist to lower the price of storage in DNA, and in a few years we'll go commercial. So in the next talk, I want to very briefly go over what Twist can go for you, what can Twist do for you. Sorry. We've already talked about a few areas, and in the next 5 minutes, I'll very briefly talk about the different products that we have. So first, starting with genes, you can go on our website. You can order your gene, clone in your vector, and we can do that for 9 cents a base, which is the lowest price possible. In the world, you get a perfect gene, and you get the plasmid, you can get the glycerol stock, and it's delivered in about 12 to 15 days for us per base. We also can do oligo pools. And so what that means is that it's a pool of oligos up to 300 base pair oligos. And the oligo pool can have 100 oligos, can have 1 million oligos, can have 10 million oligos. And so the idea is with the 300 base pair, you can explore big elements of genetic material. It could be CRISPR guides, or it could be mutations that encode for parts of a protein. And what we have is not only we have the extreme long length, but we also have an amazing uniformity of distribution. And by having a very highly uniform pool, you're going to have a high dynamic range and very low error rate in your data. The other thing that we have is variant libraries. So I already mentioned that slide for you. If you can give us a computer file with the list of mutants, we will be able to make it for you. And then last but not least, we can also do target enrichment by giving you a kit that will be able to very uniformly capture and sequence the regions of interest. And with that, I will stop. I want to thank you again for listening. Thank you for your interest. And once again, thanks the organizer for inviting me. It's greatly appreciated.
Wow, this was just amazing, Dr. Emily. Thank you so much for accepting our invitation. We're glad to have you in this historical moment of the Brazilian Symposium on Synthetic Biology. Well, after this incredible presentation, I think we can go already for our Q&A session. Wouldn't you say so?
That's great.
Okay, so the first question we have here is from Eloisa, and she wants to know that which area of SynBio are you most excited about at the moment, and which ones do you think will be the most important in the future?
Yeah, I think it's a great question because I think SynBio is absolutely going to change the world. It's going to make the world more sustainable, and it's going to make the world more healthy. And so it's hard for me to say which part I'm most excited about. Frankly, all of it. But maybe one of the things that I think are very exciting to me is synthetic biology applications where the world, the consumer, the patient does not know it's in bio, right? It's kind of like, my phone. My phone is based on quantum physics. It cannot work with quantum physics, but when I use my phone, I'm not thinking, oh, I love quantum physics. No, what I'm thinking is, I love the GPS. I know where I am. I love this application. I think it will be the same with SynBio. I think there'll be a lot of areas where people will not know it's SynBio. You and I, we will know, but I think that's when we've made it. It's once there is amazing material. The world will be that it's thanks to SynBio, and that's good.
Thank you very much. We already got someone thanking you for your presentation. Well, this is amazing. Well, let's go for our second question, shall we? This next one is from Beatriz Madeira. She said something like, what you mentioned, what are the main challenges yet to be solved in order to reduce DNA synthesis costs and make the technology more accessible worldwide?
It's a great question. That's one of the things we care a lot about at Twist, is to lower the cost of sequencing all the time, to make it more available to more people, to do more science. Already we are the cheapest, even though you get perfect DNA, right? So the quality is lower. It's perfect DNA at a lower cost. But we want to push further and data storage is helping us to, because for data storage on our silicon chip, we don't want to make 1 million oligo. On our silicon chip, we want to go to 1 trillion oligo. And so we are on a path to lowering the cost by 1 million. So they still, it's not yet, but so we don't want 8 cents, sorry, we don't want 9 cents per base. We want to go 0 cents per base. So we have a roadmap ahead of us to get there. It takes us several years, but we're working on it.
Well, I can imagine how long that can take. It's such a work-demanding process. I cannot even fathom. Well, the next one is from Leonardo Di Bortoli. Do you think DNA storage will make information more democratic, since it will be easier to make billions of copies of a specific matter?
No, exactly. I think it's a very good point, and that's one of the fit of DNA, is that you can process information much faster than on a hard drive. So if you're thinking of, if you have a data center, your Google data center, if you want a copy of the Google data center, that will take forever. Right? You have to make a copy of every hard drive. It will take a very long time. It will be very costly. But if you have DNA, the same information, with PCR is $1, 1 hour. Even I can do it. You make millions of copies, and so the processing of information is much bigger. And researchers are starting to think about what other things can we do. Copying is important, but can we do other information using enzymes? Can we do Fourier transform, for instance? Can we do a search of the data? And I think enzyme will help. And so, yes, definitely, it will be easier to process information, and eventually that is more democratic. More information, more processing is a good thing.
Well, thank you. I do agree with that. The next one is from Isis Botelho, and she said, I saw that Twist is investing in this new area of next generation CRISPR screens based on single cell. Do you think this will help to develop to develop products with this technology?
Yeah, no, thank you for the question. Maybe as a context, I like to say that we are trying to make our customers the heroes, right? We are not the heroes. We just make the tools to make life easier and more powerful for our customers, for the scientists. And so, yes, some of our customers have deployed our CRISPR screen in single cell, and that's great. And but the credit, the credit goes to them, right? They are the ones pushing the science forward, and we are there. We're there to support them. But I do believe that those CRISPR screen will be useful in developing new diagnostic tests and new therapies. But again, they are the heroes. We are not Batman. We are Robin, right? Our customers are Batman, and we are very happy to do that.
So you're not the ones making the big technologies, you're just providing the tools.
That's right. That's right.
So I think that with that, our time is up, Dr. Emily, and I couldn't thank you more in the name of all Symbio Brazil for your speak. We are all big fans of your work with DNA synthesis, and we just hope to have you here more next year, the next symposium, or next time maybe.
Awesome. Well, thank you so much for having me. It's very much appreciated, and congratulations on making such a great conference. Obrigada.
Merci. Well, bye. Thank you so much, Dr. Leproust. See you next time.
See you next time.